So in the previous video, we talked about the four properties that are satisfied by the Shapley value. In particular, the properties of symmetry, dummy, efficiency, and additivity. And there we also showed that the Shapley value indeed satisfies these properties. So in this video, what I'm going to do is I'm going to show that the Shapley value is actually the only value that satisfies these four axioms. In other words, the Shapley value is characterized by the property of symmetry, dummy, efficiency, and additivity. So in this video, I'm going to assume that you have a little bit of prior knowledge of linear algebra. In particular, I'm going to assume that you have the notion or understand the notion that in a finite vector space, every vector can be written as a linear combination of basis vectors. I'll be a bit more precise later on what I mean by this. Then I also will assume that you have some knowledge of integration by parts. And finally, now and then I will use the binomial theorem that says that a plus b to the power n can be written as this sum here from I 0 to n of n choose I. This is a combinatorial symbol of a to the power I beta to the power n minus I. And here n choose I is simply n factorial divided by I factorial times n minus I factorial. Let's start by recalling that a value function v simply gives to every non-empty coalition a real number v of s. And in total we have, for a big coalition of size small n, there are in total 2 to the power n minus 1 non-empty coalitions. Okay, so recall that the empty set value is equal to 0, but all the other coalitions have some value specified, and they're in total 2 to the power n minus 1 number of coalitions. So if we retake our example of the three-player game, we have the coalitions, all the singletons, 1, 2, 3 here. Then we have the coalitions 1, 2, 1, 3, 2, 3, and 1, 2, 3. And for every coalition, we have a value. Here it's the value 2, 3, 1, 7, 4, 5, and 10. So in other words, you can not only see v as a function from coalitions to numbers, but you can also specify v as just a list of numbers to the power n minus 1 numbers. So in other words, if you agree on a ranking of the coalitions, then you can also present v as a vector in R to the 2 to the power n minus 1. And then any vector in the space can of course be expressed as a linear combinations of 2 to the power n minus 1 base vectors. Once you determine on a set of base vectors, every vector is a linear combination of these base vectors. And now the question is, that's all fine, but which basis do we choose? And here this is, I think, one of the major contributions of Shapley, is that he was very smart in picking the particular basis that he chose. So here we're going to specify a basis. And basically, well, a basis is nothing else than a vector. And so every vector you can see also as a value function. So here he's going to use these value functions, which I'm going to call bt. So for every subset t of n, you have such a value function. And the value of this game is equal to 1 if t is a subset of S. So bts for coalition S is equal to 1 if t is a subset of S, and is equal to 0 else. These are also called unanimity games. So let me give an example. So here we have the same example again, where we have a three-player game. Here I list all the possible coalitions. And then for every coalition, you have a basis game or a basis vector. So for the singleton 1, you have b1. For the singleton 2, you have b2, and so on and so on. And now these functions here, or these vectors, take the values 0 or 1, depending on whether t is a subset of S or not. So here t is, for example, the singleton 1. Here 1 is a subset of 1, so it obtains the value 1. 1 is not a subset of 2, so we obtain the value 0. 1 is not a subset of 3, so we have the value 0. 1 is a subset of 1, 2, so we obtain the value 1. 1 is a subset of 1, 3, so we obtain the value 1. 1 is not a subset of 2, 3, so we have 0. and 1 is a subset of 1, 2, 3. So again, here we have the value of 1. And of course, you can do this for every basis vector. So for example, for the last one, you have B 1, 2, 3. The coalition 1, 2, 3 is only a subset of the coalition 1, 2, 3 itself. So this is a vector of all zeros and then one single 1. And now the claim is that these vectors here form a basis of the space R to the power 7. Okay, so in other words, if you have a value function here, this is my V, which was 2, 3, 1, 7, 4, 5, 10. This means that this vector can be expressed as a linear combination of these vectors. And in this case, you can verify that, for example, this vector can be written as 2 times the vector B1 plus 3 times the vector B2 plus 1 the vector B3 plus 2 the vector B12 plus 1 the vector B13 plus 1 the vector B23 plus 0 times the vector B123. So in symbols, V, which is a value function, can be written as a linear combination of the vectors Bt. And then, of course, you have to multiply them by some coefficients. And here I'm going to call the coefficients beta t sub t. T is here to refer to the vector. And of course, these betas will depend on the exact value of V. So it's basically a function of V. And you sum over all non-empty subsets of n. So here you can specify that T has to be non-empty. In other words, for a given coalition, so if you look at a given row, then V of S, which is here this number, can be written as the linear combination beta TV of BTS. Okay, and here, importantly, this beta TV is independent of S in the sense that it's the same for every possible coalition. Okay, so here this coefficient doesn't depend on the coalition S. So here we claimed, or at least I claimed, that this is a basis. So let's now prove this a bit more formally. So first here I'm going to prove a lemma that says that the values, or the vectors bt, are linearly independent. Once they're linearly independent, then you know they form a basis for this vector space. So the proof is by contradiction. So assume that they're not linearly independent, which means that you can take linear combinations of these vectors that will give non-trivial linear combinations of these vectors that will add up to 0. Okay. So in other words, there exists coefficients alpha t, which are not only equal to 0, such that this linear combination alpha t times bt is equal to 0. And here is this is the 0 vector. So this is a vector equality. In other words, for every possible coalition, if I evaluate this equality here at this for this particular coalition, then alpha t bts should be equal to the value 0. And now 0 is a number here. So far, so good. So let's take a coalition R. And R is the smallest minimal coalition, so it's smallest in size, that satisfies alpha R not equal to 0. And we know that not all alphas are equal to 0, so among all the ones who are not equal to 0, take R to be the smallest one. Which means that there are no smaller coalitions that satisfy the same criteria. So for every coalition that's a strict subset of R, this means that the coefficient should be equal to 0. So what are we going to do? We're going to take alpha R BRS to, or here alpha R BR to one side of the equation and put all the other terms on the other side of the equation, which gives alpha R BR S equal to minus the sum over all subsets that are different from R of alpha T BTS. With the minus sign here. And this holds for every possible coalition. Okay, this equality here. So what are we going to do? We're going to evaluate this equation for one particular coalition, which we're going to take to be the coalition R itself. So here on the left-hand side, we get alpha R BRR. And on the right-hand side, minus this sum here of alpha T BTR. So you know that BR is going to be equal to 0 whenever R is a subset of this coalition here, and it's equal to it's going to be equal to 1 if R is a subset of the coalition here, and be equal to 0 otherwise. But here, of course, R is a subset of R because they're the same. So here, this value here, BRR, is going to be equal to 1. So here on the left-hand side, we're going to have the value alpha R times 1, and alpha R is different from 0. Okay, so this is going to just evaluate to alpha R. On the other side, we have alpha T BTR, and then there's two possibilities for BTR. If T is a subset of R, then BTR is equal to 1. But we have seen that if T is a subset of R, then alpha T is equal to 0. Right? So then we have 1 times 0, so this is going to evaluate to 0 here. In the second case, when T is not a subset of R, then BTR is going to be equal to 0, so alpha T BTR is also going to be equal to 0. So in both possibilities, what we're going to have is that this product alpha T BTR is going to be equal to 0, and so the sum over all these subsets is also going to be equal to 0. So in the end, what do we get? We get that alpha R, which is something different from 0, has to be equal to something that's equal to 0. So this gives our desired contradiction. In other words, the values or the vectors or value functions BT are indeed linearly independent. So what can we conclude from this? From this we can conclude that these vectors are first linearly independent. And how many do we have? Well, we have one for every subset of n. And there are 2 to the power n minus 1 of them. So we have 2 to the power n minus 1 linearly independent vectors. So these indeed form a basis for R to the power 2 to the power n minus 1. And if you have a linear, if you have a basis, then you can express every vector in this vector space. So here V as a linear combinations of the basis vectors. Okay, so this is what to do here. In particular, for any coalition S, V of S can be written as a sum of BTVs BTS. And recall that BTS will be equal to 1 if T is a subset of S, and it's equal to 0 else. So all of these will be 0 whenever T is not a subset of S, so we basically only have to sum over all sets that are subsets of S. So we can also rewrite this as Vs equal to the sum over all sets T subset of S of BTV, and then BTS, but BTS here is equal to 1, so this is times 1. So this gives a simplification of the value for coalition S. Now, it would be interesting to not only have this expression of Vs in terms of BTs, but also it would be nice to have the value of BTV. Okay, and this is what the following lemma says, that BTV can be written as a sum over all subsets of T of minus 1 to the power T minus R, and here small t is the size of T and small r is the size of R, of VR. This is basically inverting here this equation in terms of BT in terms of the function V. An easy proof is just to observe that BT, beta T, is just a Möbius inverse of Vs. Another way to prove this lemma is simply by taking this equation and plugging in this value and then verifying that indeed, if you plug in this value here, you get the identity Vs equal to Vs. And this is what we're going to do, just to verify that we didn't make any mistakes. So what do we have? We have that Vs is a sum over all subsets, coalition subsets of S of BTV. Now we're going to use this value and plug it in here. So here we get this expression. And here we have a sum over all subsets of S, and then a sum over all coalitions subsets of T. So we're gonna, next step is gonna exchange these two summations. So summing over all subsets of S and then over all subsets of T, we can also do this by first summing over all R subsets of S, and then over all T that is sandwiched between R and S. Okay, so this is what we're doing here. Here we're summing over R, and here we're summing over T. and then of minus 1 to the power t minus r. And then vr doesn't depend on t here. Here is sum over t, so we can put it outside the brackets. And of course, we can also put it in front here, which is what we do in the following line. So here we're summing over all r subsets of S of VR. And then here, what we're going to do is we're going to rewrite the sum as a sum over the size of this set T here. So the size of the set T goes from R, the size of set coalition R, to the size of the coalition S. So it's a sum from R to S of minus 1 to the power T minus R. And then how many of these subsets do we have? Well, we have S minus R elements to choose from. And then how many do we choose every time? We choose T minus R elements. And now you can recall this using the binomial theorem. This is the same as 1 minus 1 to the power S minus R. And usually 1 minus 1 is 0, so this is 0 to the something. If S is different from R, this is 0 to some number, which evaluates to 0. But you have to be a bit more careful, because if S is equal to R, then this is 0 to the power 0, which is a strange object. But if we evaluate this as at point S equal to R, then here we have minus 1 to the power R minus R. So this is minus 1 to the power 0, which evaluates to 1. And here we have 0 choose 0, which is also equal to 1. So this indeed evaluates to the value of 1 in case S is equal to R. So all of these sums here are going to be equal to 0, except for 1 when S is equal to R. And then if S is equal to R here, we obtain Vs times 1. So finally, the only term that's left is a term Vs, and indeed Vs is equal to Vs. So we see that the values, if we put beta t equal to this value, then this expression is satisfied. Consider a coalition T and consider the value function alpha bt. So here bt is this basis value function. So bts evaluates to 1 if t is subset of S. So alpha bts evaluates to alpha if t is a subset of S. And of course it evaluates to 0 in all the other cases. What I'm interested in is in obtaining the value of phi I alpha bt. Okay, and here I assume that phi I is a value that satisfies the 4 axioms. Okay, satisfies symmetry, dummy, additivity, and efficiency. Okay, and I would like to obtain this value here for this particular game. So consider an individual that's not in this coalition T, and take any other coalition that doesn't contain I. Then there are 2 cases. So first of all, there's the case where T is a subset of S. Then if T is a subset of S, then BTS alpha evaluates to alpha. And because I is not in T, if I add I to S, then T is still a subset of S union I. Okay, so BT is union I also evaluates to 1, so this evaluates to alpha. Okay, so here I have taken a coalition that doesn't contain I. Adding I doesn't change the value of this coalition in the game. In the second case, it's also possible that T is not a subset of S. Okay, and in this case, BTS evaluates to 0. Alpha BTS evaluates to 0. And adding I, because I is not in T, doesn't help here. So alpha BTS union I is still 0. So here's the situation. I have a set S, I have a set T. T is not a subset of S, and I is outside of T. So here adding I to the set S doesn't make T suddenly a subset of S union I. Okay, so the values are the same. So in other words, what do I have here? I have a situation where I was not in T. If whatever set that I take that doesn't contain I, adding I to this coalition doesn't change the value. Okay, so in both cases, adding I to the coalition S doesn't change the value. So we know that I is a dummy player, and if the dummy axiom is satisfied, this means that phi I of alpha bt is equal to 0. Okay, so for any player that's not in T, if the player, the value for the player for this game evaluates to 0. And then from efficiency, if we add up all the values for all the different players, then we know it should evaluate to alpha BTN, okay, the value of the grand coalition. That's by efficiency. What in this case, T is a subset of N, so this evaluates to 1. So here this evaluates to alpha. But for everybody's not in T, phi I is equal to 0. So here, this sum here over all I in N is the same as the sum over all I in T. So what we see here is that the sum over all I in T of phi I alpha BT should be equal to alpha. Okay, so now the question is, how exactly are these, what are the values of this phi I? And for this, we're going to use the axiom of symmetry. So let's take two individuals in T. Well, first of all, to notice that if T is only a singleton, then we already know the value of this player is going to be equal to alpha. Okay, so let's now assume that T contains more than one individual. Let's take two individuals in T, and let's take a set that doesn't contain I nor J. Well, because I and J is in T and S doesn't contain these individuals, T is not a subset of S. Okay, that's because S doesn't contain I and S doesn't contain J. Also, adding I to S doesn't help here because S union I still doesn't contain J. So T is also not a subset of S union I. And by symmetry, T is also not a subset of S union J. So BT S union I and BT S union J will all be equal to 0. So here, the value for any set that doesn't contain I nor J, the value of S union I and the value of S union J will be equal to 0. And then, so here this condition is here satisfied, and then if this value satisfies symmetry, we know that the two players should obtain the same value. In other words, phi I of alpha BT should be equal to phi J of alpha BT. So in the end, we have that the sum here for over all I and T of phi I, that's here. Now we know that all these players in T should have the same value. So it's T times small t is a size of the coalition T. Small t times the same value for some player I and T. And this should be equal to alpha, which we had here. So just dividing alpha by T gives me that phi I of alpha BT is alpha divided by T. So in other words, what do we have? If we have this game, alpha BT, where BT is the space game, then every player not in T receives the value of 0, and then the value of the members in T is equally divided among all of them. Phi, for I in T, phi I of alpha BT is alpha over T. Now we can put 2 and 2 together. So we call that value, any value function is linear combinations of the base value functions. So V is a sum of these smaller games. And we're going to pick these here as our alpha that we had in on the previous page. So by additivity, well, anyway, we can write phi I of V. V is this sum here as phi I of this sum of games. And now we can use additivity in the sense that phi I of a sum of games is the sum of all the phi I's of the different games. Okay, so this is the sum over all coalitions of phi I BTV BT. And here this BTV is simply a number. So if we use it like the alpha in the previous page, then we have phi I of beta TV BT. What's this? It's equal to this alpha divided by the size of T, if for all members in T, and it's equal to 0 for all the members not in T. Okay, so basically this is only going to evaluate to something different from 0 if I is in T. So here we only need to take the sum over all coalitions that contain I. And what's going to be the value? The value is going to be beta TV divided by T. Okay, so basically here we have the value. This gives you the value for whenever the value function satisfies these four axioms, you will get this expression for the value, for the distribution. We can simplify it a bit further, or we can express it a bit further in the sense that we know that BTV can be written as this sum here, the sum over all coalition subset of T of minus 1 T minus R of VR. So we can simply plug it in here, and we know that, or we obtain that phi I of V is the sum over all coalitions that contain I and the sum over all coalitions that contained in T of minus 1 T minus R divided by T of VR. And here we're summing over all coalitions that contain I, and here over all coalitions that are contained in coalition T. So we can exchange the summation being as summing over all coalitions in N, and then over all coalitions that are sandwiched between R and N. Okay, so here the second summation is over T, and the first summation is over R. And of course here, the second time, you're only summing over coalitions that contain I of minus 1 to the power T minus R divided by T, and then VR can be brought outside the brackets. So now we arrived at this particular value for phi I, this rather complicated expression. And what we would like to do is we would like to show that this agrees with the Shapley value. So it might be instructive to go back to the original paper of Shapley. Basically, now we arrived here at equation 10. And then Shapley says, inserting 8, which is this expression here for the beta, and then simplifying, we get the following result, which is this equation here, which is basically the expression that we know for the Shapley value. So the only thing we need to do now is simplifying. But the simplification will take us a little bit of work to do. So here, what I have is I have a sum over all coalitions R and N. And the first thing that I'm going to do is I'm going to split it up as a sum over all coalitions R that contain I and over all coalitions R that do not contain individual I. So the first sum here is over all coalitions R that contain I, VR, and then of this expression here. So because I is already an R, I do no longer need to include it here for T, because I is an R and R is a subset of T, so I will also be in T. And then here the second sum, I have over all R that do not contain I. And then of course when I sum over T, I need to be sure that I include I and T. So here I have the first expression. And then here, this sum here, I'm going to write it as a sum depending on the size of the set T. So the size of T goes from the size of R, which is small r, to the size of N, which is N, of minus 1 T minus R divided by T. This is here. And how many of these subsets do we have of size T? Well, there's N minus R elements to choose from, because T is a superset of R. And how many elements can we choose? We can choose T minus R elements. Okay, so this is another expression for this summation here. And I'm going to call this here, this entire sum, I'm going to call it gamma of R. And then for the second one, we have the sum over all coalitions that R that do not contain I. Here, I'm going to sum again depending on the size of T. So T goes from the size of R plus 1, because R doesn't contain I, and I have to include it here in T, so T will always be 1 bigger than R. Sum to N over this coefficient here, that's the same. And how many elements can I choose? Well, I can choose N minus R minus 1, because I is fixed. And how many, these are the number of elements I can choose from, and how many do I need to choose? I need to choose T minus R minus 1, because again, I has to be included anyway. And I'm going to call this coefficient delta R. So if I take the delta R and evaluate it at R minus 1, so everywhere I see R, I just plug in R minus 1, then I have the sum here from T equal to R to N of minus 1 T minus R plus 1 divided by T. And here then get N minus R, choose T minus R. And this is almost exactly the same as gamma R. except that here we have a minus 1 to the power 1 in addition. So if you take it outside of sum, it's basically minus 1 times gamma r. Okay, so these deltas are tightly connected to the gammas. So what we're going to do is I'm going to determine this gamma r here, and then I'm also going to have the values of delta. So here, I just copied here the value of gamma r, which is a sum from t r to n of this expression here. And first thing I'm going to do is I'm going to rewrite the coefficient 1 divided by t. I'm going to write it as the integral from 0 to 1 of x to the power t minus 1 dt. And indeed, if you integrate this here, what you get is x to the power t divided by t, evaluated from 1 to 0. So this is 1 divided by t minus 0, which is indeed 1 over t. Okay, so if I substitute this here I get this integral instead of the coefficient 1 divided by t. And now in the next step, I'm going to exchange summation and integration. So I'm going to take the integral in front, 0 to 1 of this sum here. And I'm going to rewrite x to the power t minus 1 as x to the power t minus r times x to the power r minus 1. And here I'm going to rewrite minus 1 to the power t minus r as minus 1 to the power r minus t. So if you take the negation of the coefficient of the exponent here, is basically the same, because minus 1 to the power something only depends on whether this something is odd or even. Okay, so I'm just here taking the negation of the exponent, and then I can write minus 1 to the power r minus t as minus 1 to the power r minus n times minus 1 to the power n minus t. So plugging in these values in here, and then I take everything that doesn't depend on t outside of the summation. So here, minus 1 to the power r minus n doesn't depend on t, and here x to the power r minus 1 also doesn't depend on t. And here I'm left with a sum from t r to n of n minus r choose t minus r, x to the power t minus r minus 1 to the power n minus t. And here, using the binomial theorem, this is the same as x minus 1 to the power n minus r. So I get, in the end, this expression here, which gets rid of the summation. And then from here to here, notice that I again negated the exponent. But here I have minus 1 to the power n minus r and x minus 1 to the power n minus r. So multiplying these two together just changes the sign of x minus 1 to 1 minus x. So I get this. And then I'm going to solve this last equation using integration by parts. Okay, and after simplifying, we will get the expression for gamma r. So what I'm going to do, consider the expression x to the power r divided by r times 1 minus x to the power n minus r. If I take the derivative of this with respect to x, then I take the derivative with respect to the first part, which gives x to the power r minus 1, and then I copy the second part. And then for the second derivation, there's another x here. For the second derivative, there's another x here. I have x to the power r divided by r, and then the derivative of this expression is n minus r times 1 minus x to the power n minus r minus 1. And there's a minus 1 in front of the x, so I have to multiply here everything with minus 1. So if I integrate both sides, here I just have to evaluate it between 1 and 0. Now, if n is different from r, then here I have 1 times 0 minus 0 times something. So this evaluates to 0. Okay. If n is equal to r, it will not evaluate to 0, but if n is strictly bigger than r, then this will evaluate to 0. This evaluates to the integral from 0 to 1 of whatever is here, and this happens to be equal to gamma r, right? This is why we did this whole exercise. And then minus the integral from 0 to 1 of x to the power r, 1 minus x to the power n minus r minus 1, multiplied by n minus r divided by r. And if you change here r to r plus 1, basically you get this expression here. So if r is smaller than n, what do we have? We have that gamma r is equal to n minus r divided by r times gamma r plus 1. So we get this recursive equation right here. This is for r smaller than n. If we put r equal to n, well, then gamma n, we know the expression for gamma r. So gamma n is this integral here, x to the power n minus 1 times 1 minus x to the power 0. The latter here is equal to 1. And the former here, you can simply integrate it. You get x to the power n divided by n, evaluated from 1 to 0, which simply evaluates to 1 over n. So to summarize, we have gamma n is equal to 1 over n, and then we have this recursive definition for all the other values of r. So for example, gamma n minus 1 can be written as n minus 1, which is 1, divided by r, which is here n minus 1, times gamma n, which is 1 divided by n minus 1 times n, which is this expression. Can evaluate gamma n minus 2. What we get is 2 divided by n times n minus 1 times n minus 2. Gamma n minus 3, which you can rewrite in the end as 3 factorial times n minus 4 factorial divided by n factorial. Okay, so what we're going to do is we're going to prove now by induction that gamma r is equal to r minus 1 factorial times n minus r factorial divided by n factorial. And it's very easy. Gamma r minus 1, well, you just use the recursion that we had before. You multiply it by gamma r, you use the induction hypothesis, you multiply everything out, and you see that the formula works. Okay, so this is the expression for gamma r. So recall that this was our expression for phi I, was here this sum over all coalitions that contain I of VR and then gamma R, and then all the coalitions that do not contain I of VR times delta R. And we had that delta R was minus 1 gamma R plus 1. Okay. And now we have this expression here for gamma R. So phi I is the sum here of gamma R VR minus gamma R plus 1 VR. And here is coalitions that contain I, and here all the coalitions that do not contain I. So what we're going to do is we're going to simply substitute here the value of gamma r and gamma r plus 1. So this is r minus 1 factorial times n minus r factorial divided by n factorial VR minus r factorial times n minus r minus 1 factorial divided by n factorial VR. This is just copy-pasting this first part here, and then here we have all the coalitions that do not contain I, so we can associate this one-to-one with all coalitions that contain I by just including I to every set here. So we can also write it as a sum of all coalitions that contain I, but now these coalitions have one element more. So here R will become r minus 1 factorial, n minus r minus 1 factorial becomes n minus r factorial divided by n factorial. And here VR, because I is not contained, and here I is contained in R, becomes VR minus I. And now the coefficients here are the same, and we're summing over the same coalitions. So we can just join the two sums. We sum over all coalitions that contain I of r minus 1 factorial, n minus r factorial divided by n factorial of VR minus I, which is indeed the Shapley value.